Okay, we'll make a start. It's my pleasure to introduce Dr. Jonah Shaw, who recently completed his PhD at the University of Colorado Boulder with Jennifer Kay. He's actually from Minnesota, born in Minneapolis. Did his undergrad in physics at Carleton College, Minnesota, and then worked at NIST for a while as an experimental physicist. Jonah was then awarded a Fulbright scholarship to dive into the world of climate science and went to Oslo, Norway to work on mixed phase clouds in the Arctic and their radiative effects. Then he went to Colorado for his PhD, and now he's employed as a postdoc at AIRS at CU Boulder as well, working on the PREFIRE project. Much like myself, Jonah's PhD and postdoc has been largely funded by the PREFIRE mission, led by our own Professor Tristan Lequier. And now that the satellites have been in space for about a year now, there's plenty of data, and so Jonah has come to visit our building for the next 2 months. He'll be here until end of December to really dive into some of this PREFIRE data and do some really cool work. Jonah leads the model comparison component of the PREFIRE mission. It looks at these really interesting questions about how we compare reality to observations to models. What else has Jonah done? Got some work there. Yeah, so feel free to reach out to Jonah. He's very much an expert in climate model radiative transfer, satellite simulators, sort of these apples-to-apples comparisons and how we compare to climate models. He's also a keen cyclist and cross-country skier. In his first week here, actually Jonah biked down to UW-AOS from here to get spotted cow straight from the source. So I hope you enjoy your time here in Madison, and take it away.
Awesome. Thank you so much for the introduction, and thanks for coming. So yeah, I'm Jonah. I'll be here until around AGU. And like Hamish said, I've been working on the NASA PREFIRE mission for a while now. And I'm excited to be here in Madison, where so much of the satellite meteorology and climatology happens. So I'll be talking about model observation comparisons today. And model observation comparisons with surface temperature, with spectral radiation, with broadband radiation. But I am going to be often approaching these topics from the perspective of detection and attribution work. And so this means taking those observations and saying something about them in the context of kind of internal climate variability or the natural fluctuations of the climate system. And so I just want to put this in a bit of context using the last few IPCC reports. So the IPCC language, as we can kind of expect, has evolved over the last 3 executive summaries and reports. And this language can give us some kind of ways of thinking about detection and attribution. So if we look at a statement from the 4th assessment report, it talks about predictions, saying that emissions resulting from human activities are substantially increasing atmospheric concentrations of greenhouse gases, and that these increases will enhance the greenhouse effect. And so, like I said, this is about prediction, but kind of thinking about it in this model and detectability framework. Prediction, in the sense of a model, means taking our Earth system model that is, one way that we understand the climate system, increasing greenhouse gases, and then seeing that our global mean surface temperature increases. The next IPCC report made a statement that's more about detection, saying that warming of the climate system is unequivocal and that many of these changes are unprecedented over decades to millennia. And so, as opposed to prediction, detection is this question of taking our observations, which are in this solid black line here, and saying that they are not statistically consistent with kind of the normal evolution of the climate system. And so how we model this is we take our system model, we force it with kind of the expected forcings of aerosols, greenhouse gases, volcanic eruptions, and then we quantify our null hypothesis by removing the anthropogenic contributions to that system and showing that these two behaviors can be distinguished from each other. And I think this word unprecedented is really kind of the trigger of saying that we're doing detection. It implies this comparison between natural climate variability and the force signal. Most recently, the 6th assessment report in 2021 stated that human activities, principally through the emissions of greenhouse gases, have unequivocally caused global warming, with global surface temperature reaching 1.1 degrees centigrade above a pre-industrial value. And so this is finally about attribution. And so attribution kind of combines all these different frameworks that we've been talking about. And so in addition to showing that our observations are inconsistent with internal climate variability, we run our climate model with these both combined natural and anthropogenic forcings, and we show that effectively we need all of these ingredients in order to explain the observed behavior. And so this framework, we can apply it to global mean surface temperature, but we can apply it to many different climate questions or climate processes that we might be interested in studying. And overall, there's a lot of science in detection and attribution, and what it tells us is that our planet is undergoing rapid and detectable changes. And this is just one more example, looking at loss of Arctic sea ice, where again, we quantify our pre-industrial variability with one model simulation. We take our observations and we show that they're consistent with our model with kind of combined anthropogenic and natural forcings. And so this kind of wealth of literature is showing us this planet that in many different ways that we can slice it, that we can look at it, is that this change is happening and it can't be explained by natural climate fluctuations. But of course, there's a lot more to be done in this detection and attribution space, and that specifically relates to specific climate processes and seasonal or regional change. And this example, I think, is a really good demonstration of that, which is that this map is showing the year at which we expect to be able to detect a change in precipitation, and we now have this nice kind of spatial map of these years in which we'd be able to expect to detect a change. And these two color bars, the red and blue here, indicate that a detectable change is an increase in precipitation in blue or a decrease in red. And so clearly there are different climate processes going on here, and there's very different timescales at which we'd be able to detect a change. And the reason we're interested in detection and attribution is because, first and foremost, this is a really intuitive way to communicate climate change outside of science, to say that a change would not have occurred in the absence of human activities. But also, this idea of detectability is also just intuitively related to adaptation. Our systems, our infrastructure are all built, largely to withstand the variability in the current climate state. And so to say that a change is detectable is often equivalent to saying that adaptation is needed. And so I also want to say that model observations really underpin this detection and attribution framework, but they're also just fundamental science in and of themselves. And so this is an example of our kind of climate model evaluation with observations using series, so our broadband measurements of incoming and outgoing shortwave and longwave radiation. And what I'm comparing here is model error in both our shortwave and longwave cloud radiative effect, where we take our clear and total sky broadband radiation fields and we difference them. And we're looking at error through 3 generations of the community atmosphere model, which is an atmosphere model that is the atmospheric component to a community or system model developed at NCAR, and that we'll be using a lot in this talk. And so if we look at these kind of measurements of our cloud radiative effect, we can see that the model error decreases in both shortwave and longwave monotonically from the 4th to the 5th and 6th generation of these models. And so if we kind of take this at face value, we would say that, oh, our models are improving. Our representation of these clouds in these models is improved. But actually, if we make another comparison, this time of cloud fraction, and we compare against 3 independent measurements of cloud fraction, we see a different story, which is that our cloud fields have improved from the 4th to the 5th generation, but all of these different observational records show that the representation of clouds in this model actually got worse between Camp 5 and Camp 6. And so our model observations are fundamental science because our ability to make these comparisons in a nuanced way, which I'll say that this kind of comparison does, it uses a satellite emulator tool, which is not kind of a common comparison that we do with our models, but enables to give this kind of more in-depth, nuanced comparison, is just really important for evaluating our models and determining if they're fit for task. So to kind of jump into the meat of this talk, I'll be talking about model observation comparisons through kind of these 3 ingredients, which are our Earth system models, our observations, which will be both satellite and in situ. And then the third ingredient is the actual methods that we use to make these comparisons. And so this is really just, I've kind of repurposed my PhD defense, and so the framework here will just be in the 3 chapters of my thesis. And the first chapter is all about detecting changes in Arctic long-wave radiation here. And the motivation is kind of, before jumping into PREFIRE observations, what can we learn about our broadband long-wave radiation in the Arctic or maybe in polar regions in general? And this will really focus on introducing some new methods for looking at change detectability, leveraging large ensembles, and also, so this is more a models and methods focus. And this work was published in Journal of Climate in 2023, and we're looking at the different seasonality of the detectability of these long-wave radiation changes. And the questions are, effectively, when will our Arctic outgoing long-wave radiation, our OLR, when will these changes emerge from internal climate variability? But also, really importantly, what are the climate processes that mediate this time of emergence? And I'll be using the Community Earth System Model, CESM, and then those broadband long-wave observations from the CERES satellite record. And even though we'll be looking at Arctic climate change from the top of the atmosphere, it's really important to kind of start and ground ourselves at the surface, because Arctic climate change is this really kind of surface-focused process in a lot of cases. And specifically, 2 indicators of Arctic climate change are sea ice loss and surface warming. And so here we're just looking at these kind of trends observed over a 21-year period in month on the x-axis and latitude on the y-axis. And essentially all we're seeing is sea ice loss. It occurs throughout the year, but it's greatest during the melt season, and it maximizes at the sea ice minimum in September. And we can effectively see that our sea ice loss is occurring on the edge of the ice pack by seeing this kind of inverted U shape, as the ice retreat is faster, and also the ice grows back more slowly in the fall. When we look at surface temperature, it actually really complements our sea ice loss, which is that surface warming is occurring, again, throughout the year, but it's maximized in times when we're not seeing sea ice loss. And the reason is just a really simple energetic argument, which is that when we're melting sea ice, the energy absorbed by the Arctic climate system is going into these latent heat changes rather than changing temperature. And so our greatest increases in surface temperature are occurring in the fall and through the winter when we have really consistent sea ice in the Arctic. And so the reason I've shown these kind of surface changes is that they really explain what's happening at the top of the atmosphere, which is that our loss of sea ice reduces the albedo. We now see trends in absorbed shortwave radiation from CERES. These are absorbed shortwave and longwave radiation trends from CERES. And then we radiate more effectively as a warmer black body, and our outgoing longwave radiation increases are really well correlated with those surface warming. And there's effectively previous literature on the detectability of all 4 of these signals, except for the outgoing longwave radiation, which is what we'll dive into here. Yes?
Sorry, can I just ask, is the absorbed shortwave over the ocean only, or is it not an ocean?
So everything here, great question, will be 70 to 90 north. So we don't mask out non-ocean cells, but we're in kind of the central Arctic where the surface type is almost entirely ocean. Yes?
Why is the absorbed shortwave lagged behind or ahead of the change in sea ice concentration?
You're looking at the overlap?
Yeah, like the absorbed shortwave goes from like AMJ through JJA, but the sea ice concentration doesn't really kick off until JJA.
Yeah, so insolation explains a lot of those factors, and just that we're getting more insolation at the lower latitudes. And that's kind of, or I guess that's more of an explanation in the fall why we don't see the associated increase in absorbed shortwave radiation. You're pointing out this region here.
No, just your comment was that we're seeing more absorbed shortwave, which is coincident with the reduced sea ice concentration. The absorbed shortwave radiation is leading the sea ice concentration.
It's slightly, but I'd say that it's largely explained by the loss of sea ice. But there are other factors, like the surface albedo changes before the sea ice itself is actually lost. Or thinking about melt ponds or changes to the snow morphology. I'll kick it to that. Yes?
I'm also a little confused about the surface temperature and sea ice concentration percentages per year. It looks like surface temperature increase spans September, October, November mostly, and the sea ice concentration decrease kind of overlaps substantially with that. So I'm not sure I
Exactly.
understand that.
So in the fall, you have this kind of combination of factors, which is that you have less sea ice because it's warmer. And so the factors are slightly different. You're not able to form sea ice because you're still losing that heat from the ocean surface into the atmosphere and into space.
Okay.
And so that's where they don't kind of need to offset each other because they're actually representative of the
Okay.
same process.
Okay.
Great question. So we're looking at this outgoing long-wave radiation. We're asking, can we distinguish it from internal climate variability? And I'm going to focus, kind of collapse our spatial dimension here and think about just the monthly fields and compute trends for these months, and then quantify internal climate variability using a long pre-industrial control simulation from the community year system model version 1. And so what we're looking at here is those monthly observations of trends. This is 2001 through 2021. And then our blue confidence intervals effectively say, for trends of the same length from our pre-industrial control simulation, what is a 95% confidence interval? So this is quantifying just the natural fluctuations of the pre-industrial climate. And the conclusion here is that, at least as of 2021, using this framework, we weren't able to detect changes in this outgoing long-wave radiation. We have 1 month. You'll notice it's October, where we are outside of that 95% confidence interval. But I think looking at 12 months and seeing one outside and the rest fall in does not give confidence to conclude that we're able to detect these changes. And so this kind of null result really motivates the kind of questions going forward, which are, when will this outgoing long-wave radiation, when will these changes be detectable, and what are the climate processes that mediate detection? And so we're going to leverage the large ensemble now that we've kind of used our observations and not found detection in order to answer this question. And so this is just an example of a variable of sea ice fraction to illustrate the methods that we use here, which is that we have 1,800 years of pre-industrial control simulation from our model, and so we can grab one 50-year segment from this 1,800-year record and look at any variable in the fluctuations in it. But of course, we can grab many different 50-year slices from that pre-industrial control, and they're going to tell us something about the mean invariance of our changes. And if for each one of those time series we start at 3 years, compute our linear best fit, add a 4th year, recompute our best fit, we can see how trends actually evolve in time as a synthetic record now observing the pre-industrial would evolve. And so now we've kind of transitioned to this trend space, so we're looking at our trend as a function of trend duration, and we can see that in our pre-industrial control simulation, for short durations, we are equally likely to see large positive or negative trends in sea ice fraction. But as we observe for longer, we kind of center around the stability that is this pre-industrial climate. And so this blue envelope is quantifying that pre-industrial variability. And what we add to this is our large ensemble, where now we have 40 different realizations of our Earth system model, and they're all evolving due to different internal climate variability, but now they're forced by increases in carbon dioxide and other anthropogenic forcings. And so the differences between these different ensemble members quantify internal variability, but again, in the forced climate. And so we calculate trends in all these ensemble members to ask, what is the detectability of this signal? And so for each ensemble member, we get a year at which the trend exits this envelope of internal variability and doesn't return. And this is kind of our detection. But since we have 40 different realizations, we can look probabilistically at when this detection actually occurs. And so we can construct this cumulative distribution function, which is basically telling us that, sure, we could detect this change in 20 years of observations, but we could also detect it in 40. And so we now have this kind of probabilistic distribution of our detection variable. And so we repeat these methods for all 12 months of the season, and we're able to now plot a 95% confidence interval, which is basically demonstrating that PDF of detection for our different months of the year. And so what we see here is that there's a large seasonal cycle in the detectability of our outgoing long-wave radiation variable. In the fall, it's much earlier than it is in the spring. And so there's about 20 years of difference between when we would expect to be able to detect these changes. But also, these 95% confidence intervals, they really quantify just irreducible uncertainty in when we'll be able to detect this change. And so even in the earliest months, in September and October, we have 20 years of uncertainty. And when we move into the spring, that becomes something more like 40 years of uncertainty. And so there's just this really large irreducible uncertainty in when we expect to be able to detect this change. This horizontal line indicates the length of the series record, which is now ticked up. It's more like 25 years now. And it basically tells us that there's some overlap in almost all months of the year. And so there is a realization of the climate system in which some of these changes were detectable for almost every month. And of course, you might ask, well, what about the climate processes? All you did was show me this with one climate model. Well, we kind of get at that question by repeating this analysis with an additional climate model large ensemble. In this case, we're using CSM2, the next generation of this model, and specifically, we're forcing it identically. And so this is forced with the CMIT5 forcings, and so the only differences between these models are in their physics. So we can try and understand the kind of climate system-driven impacts of this result. And the error bars here are just enable us to make comparisons between these ensembles. They are different sizes. The CSM2 ensemble only has 10 members, so we need to use bootstrapping to look at our statistical differences. But essentially, this second ensemble actually is showing largely the same behavior, but the differences occur in the fall, and the second ensemble emerges later. So these detectable trends occur later in the record. And so we see that CSM2 is emerging later in the fall, and we want to understand what are the climate processes that mediate this. And so I won't go through kind of all of this search, but what we find is that shortwave absorption during the summer is actually really mediating the changes in the detectability of these longwave radiation changes during the fall. And so specifically, our second ensemble, CSM2, absorbs shortwave radiation more slowly than our initial ensemble in the fall. And this leads to a smaller increase in the emission it absorbs more slowly during the melt season in the summer, and that emits more slowly in the fall. So this kind of gets back to the question earlier, which is that the changes in the fall are really the result of all the absorbed shortwave radiation during the summer, which then has to be emitted before sea ice can freeze. And so it's really these shortwave effects, again, happening at the surface with the change in albedo that are kind of the answer of the kind of process-related aspect of our question. And I won't weigh into whether one of these models is better or worse because, as you can imagine, one of them is better in one way and the other is better in the other. And so if we're thinking about physical reasons why this is occurring, CSM1 has a more realistic representation of pre-industrial sea ice. And so part of the reason it absorbs shortwave radiation more quickly is it has more sea ice to lose. But also it loses it more rapidly because it doesn't have as good of a representation of reflective liquid clouds. And so that loss of sea ice is less buffered by the cloud response. And so again, I won't weigh in, but these are the climate processes that are really mediating the shortwave radiation budget and kind of determining our question. So to just summarize, we see this kind of strong seasonal contrast in that our fall outgoing longwave radiation changes are emerging before the spring changes, but there's this really large irreducible spread that we quantify with our large ensembles. Also, the seasonal patterns of force change of internal variability actually determine this time of emergence. So the reason that we see the earliest emergence in the fall is not that the trends are most rapid then, they're most rapid a little later in winter. And it's not just that the variability is low. The variability is lowest during summer when we have kind of the most ocean surface available to mediate temperatures. The fall is this kind of Goldilocks zone where we have pretty rapid changes occurring, but we also have relatively low variability. There's plenty of ocean surface, but there's also all this accumulated heat that's returning to the atmosphere. And then finally, by comparing these large ensembles, we showed that the shortwave energy budget during the melt season is really the process that's controlling a lot of these time to emergence values. So we're talking about broadband radiation, but I'm going to pivot now and talk a bit about spectral radiation, but we're going to stay in this kind of infrared or long wave framework. And specifically, I'm going to present this tool that I developed that allow us to compare spectral radiation observations that are made by an instrument like AIRS or PREFIRE to our Earth system models like the ones that I used in this last section. And so this work was published earlier this year in Geoscientific Model Development. And what it really is a tool for system models that allow us to make these apples-to-apples comparisons with kind of direct level 1 observations made by satellites, by infrared sounders. And the questions that we wanted to answer here were, how do we compare these direct satellite spectral radiation observations with Earth system models, but also what kind of new science is enabled by the ability to make these comparisons much more easily than we have before. And I want to start with a philosophical footnote. I think this was a year and a half ago. Gavin Schmidt, who's the director of NASA GIS, was giving a presentation at a workshop about model observation comparisons, and he presented this kind of keynote through the frame of several philosophical footnotes, and I really like this one. And it says, all observations and comparisons are based on models too, or in other words, it's models all the way down. And what this really means is that many of the data products and the quantities that we treat as observations are themselves produced by a model or through some steps of inference, and they're not actually direct observations. So we need to be really aware of this when we're evaluating models in comparisons. And so one example of how it's models all the way down is actually these broadband fluxes from Sirius, which I think we often think of as an almost direct observable value. But Sirius actually, like this kind of cartoon satellite up in space, is observing just a narrow solid angle, and then it's reporting something about kind of the integrated over the hemisphere radiated value. And so it's measuring a radiance, and it's reporting a flux. And what it uses to actually convert between these is called an angular distribution model that takes this radiance, it says something about the orientation of the satellite and the scene type, and it applies this conversion factor. And of course, that's a model that allows us to make that comparison, and yet we often, don't think of uncertainty when we think of series observations. And if you can find somewhere where those uncertainties are reported, I would love to talk to you. Another example of how it's models all the way down is, by comparing our reanalysis and satellite retrieval products. And specifically, we can take reanalysis and satellite retrieval products that ingest even the same set of observations and show that they're different from each other, which implies, this kind of underlying uncertainty in the ways that we infer geophysical variables from spectral observations. And so one example is just looking at trends over this 12-year period between two different retrieval data sets. And these are actually both based on the same instrument, the NASA AIRS instrument that I'll be talking about later. And there are two different teams in NASA, one ClimCaps, other AIRS V7 are the products that these two teams produce. And yet, if we look at the water vapor trends over this 12-year period, we get completely different pictures of what's going on. And if you ask, well, what about reanalysis? What about AIR5? It's much more complex. It ingests a lot more observations. Well, if we look at the AIR5 trends, they also look really different over this period. And so I think that this is a really good illustrative example of how if we have differences between these data products, they imply these large structural uncertainties that are really important are not quantified. And they're not quantified because it's really hard to quantify uncertainty in these kinds of data products. And so what we want to ask is, what if we want to complementarily compare? We want a complementary comparison that compares our models directly with these observations and rather than these inferred values. So we're going to compare these spectral radiation observations that are kind of really go into what these products output, and we're going to compare those observations. And of course, making these kinds of comparisons is challenging. There's a reason that we don't do it before. And the reason, first and foremost, is because it's not intuitive. But also, there's these barriers of how we define variables that we observe versus the variables that our models output that make these comparisons also really challenging. And so, just kind of to start, what we observe from space are radiance fields. And these are not comparable with model fluxes. Our Earth system models are not computing these they're not computing radiance fields, which again, have to do with a specific solid angle. They're computing heating rates and radiative fluxes that are integrated because that's what the model needs to iterate its physics. But there's also differences in how our satellites observe, diurnal sampling, spatial resolution, how things like clouds are handled. And so all of these definitional differences make it much harder to make these comparisons. And what we want to do is introduce a tool that allows these comparisons to be much easier. They shouldn't require a lot of expertise with radiative transfer model if you just want to evaluate your model and you're not a radiative transfer expert. And so I'm going to present this tool and then present some comparisons with two different sets of satellite observations. The first is the NASA AIRS instrument, which is on board the Aqua platform, which has been up since 2002. And the second is PREFIRE, which we now have just over a year of observations from. And so how are we going to bridge this gap? How are we going to bring together the different kind of variables that our models have and our observations have? Well, we're going to rely on a tool that already exists and already exists in our Earth system models. So we're going to start with the climate model, or our Earth system model, CSM2. This is just iterating our understanding of the physics of the climate system. It has an atmosphere component, an ocean component, sea ice, etc. And all these components are interactively kind of iterating to evolve our system. Unfortunately, this model also has a satellite emulator tool called COSP. And so you can think about COSP as this little package that sits within the climate model, and it's able to look at the instantaneous model state. And so it can see our profiles of temperature, of humidity, kind of throughout the model at any point in time. And so it takes those properties of the surface and the atmosphere, and it passes them through these emulators that say, what would an instrument like Calypso see? What would an instrument like MODIS see in terms of clouds? And so if you think all the way back to those kind of comparisons of cloud rate of effect and then cloud amount, this is the tool that allowed us to make those more nuanced comparisons. But what this tool doesn't do is compute those radiation fields. It kind of does the retrieval on its own, and so we get some of the definitionals, or the definitions resolved, but we're not actually going to this radiation comparison. And so what we add here is a fast radiative transfer model. It's called RTTOV, RTTOV. But really what's important here is that, again, it's able to sit in the model and pass the model state through a radiative transfer model to obtain clear sky and all sky radiance or brightness temperature fields that are consistent with the spectral response functions of an instrument that we might want to be able to compare against. And so what we get here is both consistent with the optics and the measurements of the instrument using this radiative transfer model, but also consistent with the physics of our Earth system model in that we're able to look at the instantaneous model state and look at fields that we don't have in often offline output, like cloud, like vertical profiles of cloud mass, mixing ratios, ice and water profiles. And so we have all this tool, but what do we get from it? And I'll say that the summary is just, we get satellite-like spectra that also, if we think about them and really try, we can get intuitive meaning from them. And this is just the simplest example. We're looking at the surface temperature field in our Earth system model on the right, and then we're looking at a really transparent region of the spectrum, and we've simulated brightness temperatures from this instrument on the left. And so they're basically identical just because this region sounds the surface, but on the left, this is actually passed through that radiative transfer model. And so this is an observable like quantity. You can think about it as like a level 1 radiation, brightness, temperature, radiance field, but it's a level 3 variable in that we now have it in this gridded field, so we can compare. And so this, again, is just about the simplest example we can think of, but we can look at proxies for other fields. And so we can take a channel that sounds the upper troposphere, and we can compare it to what the model says about temperatures there. And the goal here is not to derive a one-to-one relationship. Our retrievals tell us about the relationships between these fields, but that there's still a lot of intuition in this direct observable space. And so we can even go and think about things like clouds and just construct a really simple proxy for clouds by taking the thermal contrast between clear sky and all sky channels. And so we can effectively reproduce, at least outside of the high latitudes, our cloud fraction through this really simple thermal contrast. And so once we've set up these variables, we can make comparisons between our observations and our model. And so in this is this 741 centimeter inverse channel. What matters is that it samples upper troposphere, and we can compare observations from, again, more than 20 years of AIRS with what our simulated radiance field from our model is, and we can show that we're seeing the effects of CO2 forcing in the negative trends in both these channels, but also we can immediately identify a cold bias in our model. And I think we can unambiguously identify this bias because we don't have those retrieval uncertainties. This is just a really straight comparison between these fields. And then if we kind of repeat that comparison with our proxy for clouds, we can say that this thermal contrast field, our model actually has a pretty good representation of it over this period. It's getting both the variability right and also some of these kind of interannual fluctuations as well. And so that's how we can kind of leverage this tool in order to evaluate our models, but we also want that street to go the other direction. We want to leverage the predictive power of models in order to benefit our observations. Yes?
Sorry, quick question. I don't know anything about this, so that's probably totally naive. How do you know that the error is in the CESM on the left and not in the AIRS retrieval?
So, that's a great question. The AIRS instrument has kind of basically a long time of observations, and the team that has been looking at it are able to compare. What they've done basically is taken observations, direct observations of trace gases, specifically CO2 in situ, and shown that the trends that AIRS observes are really, really consistent with relatively what we'd expect from the increases in those gases. And so AIRS has many hundreds of channels, but there's definitely a subset still of many channels where they've validated the trends in it to a degree that is far, far below what we see here.
But the trends are the same, right?
The trends are the same. And so the trend here is due to CO2. So this is basically, we're in the troposphere where our lapse rate, temperature gets colder as we go up. As you add CO2, you push your emission level to a colder isotherm.
Right, but as I understood it, Till was asking about the bias. How do you know whether the AIRS estimate is biased or the CSM2 estimate is biased, or do you not know?
I trust the AIRS team, basically. Yes.
I think to clarify, that is not a retrieval, that's a measurement. That is the level 1B AIRS measurement. And there's been all sorts of comparisons with IASI and CRIS, et cetera, that they have characterized that measurement. It's not a retrieval.
Thank you. Yeah, so we can both evaluate our models with this tool, but we can also, again, kind of drive the other direction in our model observation street and say, what can models contribute to our satellite observations? And so what we're doing here is simulating 4 different channels of the PREFIRE instrument. And this is over a 2 or 3 decade period at the end of the 20th century. But we're basically seeing how do these fields evolve in time. And so we're quantifying both the mean state of these fields, but also the interannual variability of them. And this simulation actually has been extended through much of the 21st century. And so I'll just skip to the end, but again, we're quantifying the variability in the force trends in these fields so that we can take a mission like PREFIRE, which, because it's a CubeSat platform, will not be up for as long as AIRS, and we can start to understand the interannual variability that we might expect in these observations. And so that's exactly what we're looking at here. So this is one far infrared channel from PREFIRE, and we're looking at the zonal mean anomaly in brightness temperature, and then a zonal variant, where we're just kind of taking the variance across a constant latitude region. And these black lines here are 20 different years from our model. And so we're now quantifying the interannual variability so that we can put that single year of PREFIRE observations in this broader context that the model is able to provide. And so to summarize, this tool simulates these satellite-like spectral radiation fields directly in our Earth system model. And we're able to both evaluate model performance against direct observations, but also we can support future satellite missions by simulating them ahead of time or kind of in process as something like an instrument like PREFIRE is making these observations. I'm now going to, yes?
One quick question before we go on. I missed which version of CSM2 you were doing in that section. Was it the usual fully coupled version of CSM2, or was it some other configuration?
So I'm taking CSM2, and in order to save compute time, I'm running it and I'm supplying the boundary conditions from a fully coupled experiment to the atmosphere only.
So was FCOM set?
Yes. So it depends on which experiment, but basically I'm running an AMIP simulation and then I'm branching to an SSB simulation.
Thank you.
Yes.
So a follow-up to that, when you compare the interannual variability between AIRS and CSM2, which had an annual component to it, what are you forcing CSM2 with any observed constraints to have that apples-to-apples comparison? So if you go back to slide 35.
Oh, these might be bouncing around. I guess I never corrected my slide numbers.
Okay, can you go back 2 slides from this slide? One more.
Here.
Yeah, so here, the year 2004, 2020, in CSM2, is that coming from the free running CSM2, or it has some kind of observed constraints that you can be very
Yes.
accurate?
The reason we're getting the interannual variability here is I'm also both supplying observed boundary conditions and I'm nudging to reanalysis. So the meteorology is constrained as well.
Okay.
Is that the case for all of this? Is it in general? Sorry, is that the case for all of your all of this here, or just this particular?
It's also true for this one, but of course when we forecast in the future we can nudge.
Yeah,
Sure.
Yeah.
Thanks.
Great. Any more questions before the next section? Yes.
I mean, I guess the reason why I think this is why that's kind of an important question. Like if you go back to the previous thing that you were just showing there, like no, one forward. One forward. Let's keep going forward, and then one more. And there we go. Right. I mean, there are large biases from these models, and you're showing that they match really well. If that's coming from a CESM standalone simulation, that you're then using the simulated SST as an AMIP, then it's a very different response to that than if you're using observed and nudging.
Yes, and this actually is not nudged.
Okay, that's a surprise.
I should have a table. I should have a table somewhere. But I will say that these fields, and this is kind of how the sausage gets made. You'll notice they are zero. I've removed the mean.
Okay.
So this is just showing that the spatial patterns are very, very similar. It's not showing biases, like constant offsets.
Since people are asking questions now and you don't seem to mind, I'll just ask, so how is this different than a satellite simulator?
It is a satellite. It is a satellite simulator. And what it's doing is it's doing radiative transfer kind of more detailed than at least COST does. COST is really simple radiative transfer. And then it's not doing the kind of inversion or retrieval process. So what COST does is it says, what would Calypso see? So it looks at like what is the attenuation, and so the LiDAR can't see deeper than that, and that's how it constructs its cloud fields. Here we're just performing the radiative transfer, and then we're returning the brightness temperatures or radiances.
Okay. Gotcha.
Okay, now for something very different. So, I think I mentioned it earlier. I don't know what the uncertainty of series is. And when I was working on that chapter, I was frustrated by the lack of uncertainties from series. And the only reference I could find to series uncertainties was one paper, and it just referenced personal communication with one of the scientists. And I don't mean to, series is really an incredible data product. All of the information that they take in, and also these angular distribution models, they test them a lot, and they're really complex. I don't mean to criticize these fields, but again, there's a modeling component, and I think there should be an uncertainty reported, especially for an observational, climate data record that is so widely used in so important series. And so I didn't find that uncertainty product, but I met a postdoc at CU who had created an uncertainty product for historical records of surface temperature from in situ observations. And so I decided to ask, well, I'm just going to see how does that uncertainty influence our ability to detect changes in regional surface temperature. Because I couldn't do it for the broadband top of atmosphere radiation, I decided to do it for a different variable. And so this work was published earlier this year in Environmental Research Letters, but effectively what we're interested in is regional warming and different sources of uncertainty that create spread in actually when we expect to be able to detect regional warming. And the reason we're looking at regional warming is that is where our climate impacts happen. It's definitely, the Earth as a whole is definitely warming. We definitely know why. But when we go down to these finer scales, it becomes harder. Internal variability is larger. Observational uncertainty can be larger. It's just a more challenging question. But actually, if you go to the most recent IPCC report, there's a figure in the executive summary that tells us what this time of emergence, or the year at which we expect to be able to detect a change in surface temperature is for these different IPCC regions. And all of these regions have a value, which is basically to say that they are telling us that we can detect these changes, and so maybe the uncertainty is not very important. But this is actually just the first panel of a two-panel figure, and the second panel repeats the same exact analysis, but with a different data product. And now we have a lot of these different IPCC regions that are grayed out, so they don't have a value. There's not enough data to detect a change. And so I think similar to comparing our reanalysis and our satellite retrieval products is that this difference, when you perform your analysis with different data products, implies this unquantified structural uncertainty. And so we want to ask, where are observed changes robustly detectable? And also, how do observational and model uncertainty influence the detection of regional warming? And we're going to take a slightly different methodological tact from the way that these were computed. These time of emergence values were computed only from observations. We're going to leverage our model as well. So that's why we're interested in both the model and the observational uncertainty, essentially. So we're going to use a slightly different methodology. But the methodology is going to look very, very similar to that first section where we're looking at our time of emergence from our climate model large ensemble. And so we're going to think first, we normally think about our temperature record as being deterministic, but it's probably better to think about it deterministically. And so instead of at every kind of region and every point in time we have a single value, we can have a distribution of values. And here we're going to quantify them. This is actually 200 different realizations of our surface temperature. So you have this historical surface temperature record. And this actually comes from the NASA GISTEM. So we have these 200 different realizations, and then we treat the probabilistic record as just the median value across all of them. And so we can take each of these 200 fields, and just like we did for those 40 different ensemble members, we can compute the trends as our observations increase in duration. And so that's now what we're looking at here. We've moved into this trend space, where we're now looking at our trends as a function of the end year, or the duration of the trend. And we're using our pre-industrial control simulation to quantify that internal variability, just like we did in the first section. Yes?
How does NASA GIST produce the 200 different realizations?
I have an extra slide for that, and I'm happy to show it to you at the end.
Looking forward to it.
But it's complex. I didn't do it, and there's a paper on it, and I'm happy to show it to you.
Yeah, I don't really care about the details, but I mean, are they just like subsampling? It's like Monte Carlo sampling, or what are they?
They make different assumptions about offsets that stations might have, about the degree of kind of spatial and temporal correlation. So we take like these point observations, how representative are they of the broader area? They do a lot of different things. Yes. And so we now are in this space where we can look at 200 different ways that our trend may have evolved and may have become distinguishable from internal climate variability. And so we can think of this kind of normal or median time of emergence COE value is when that deterministic record is detectable, and then we can define a strict time of emergence when 95% of those 200 ensemble members have emerged from internal climate variability. And really, the difference between these two is that uncertainty that's kind of imparted by observational uncertainty, and that we're able to quantify with this probabilistic temperature record. And so we're going to perform this analysis with all of these different IPCC regions, and first quantify that median time of emergence, just like that IPCC plot showed us. And then we can quantify our strict time of emergence. Our colors got a bit lighter. They're later because of uncertainty. And then the delay, of course, is the difference between them. And so in some of these regions, this delay is quite small, some order of 0 to 5 years. And in other regions, the delay is in excess of 1, 2 decades, and even longer than that. And so, this is a summary of all of these different ensemble members and comparisons, and you might ask, what are the actual reasons that we're seeing these large delays? And to kind of demonstrate more anecdotally why this is occurring, I'll just show you 2 different regions with pretty different behavior. The first is this West and Central Europe region, and we say that this is characterized by low uncertainty and monotonic trends. There's low uncertainty because the spread of our ensemble around the determinist record is really small. And so when our trend pops out in internal variability, they all basically pop out at the same time. But there's also fairly low, the trends are fairly monotonic. So our trends are pretty even, and then once they really start to increase, it's very steady. There's definitely, decadal variability that we can see in this record, but it's not as massive as it is in some other regions. And so this comparison is this region, the IPCC Southeast Africa region. And here we both have larger uncertainty, but also our trends are not as monotonic. And so the spread around that median value is much wider. We can see just kind of the width of it. But also we have this kind of local maximum in the warming rate that occurred in the mid-20th century. And then we had this decrease in warming for about 30 years. And so this leads to the median trend actually being detectable much, much earlier than the kind of strict time of emergence that we had. So some of these values are just staying in that envelope of internal variability. And really what we're seeing is that this decrease in trends is aligning really well with the decrease of the envelope of internal variability. So the leverage that we're getting from our longer record is being offset by this decadal variability that we're seeing in the observations. And so it's the combination of these two factors that gives rise to that kind of like pattern of delays that we're looking at in the last figure. So these non-monotonic trends and areas where we have low observational quality and higher variability. But of course, there are other sources of uncertainty here. I've used one Earth system model, and then I've used one observational product. Sure, it gives us 200 different realizations, but they can also share common biases. And so we want to quantify a much broader sense or scope of uncertainty in this time of emergence value. And so we introduced an additional 3 Earth system models. We're using 4 models here. Each of them has an associated large ensemble, and that has been used in a separate study to basically validate the internal variabilities of these models. So that's why we're using specifically those 4. And we use an additional observational uncertainty product. And this is the Hadley Center product. And it also has 200 different realizations. And so now if we have 4 different ways of estimating internal climate variability, and then we also now have 400 different realizations of historical surface temperature, we can mix and match those to estimate for each region 1,600 different values for time of emergence. So we get some nice statistics now that are now quantifying the spread, not just due to our observational uncertainty, but also our model uncertainty and uncertainty between these products that estimate our observational uncertainty. And so if we recompute our median strict time of emergence and this delay, we can see that our delays are now much shifted towards values in excess of 1 or 2 decades. And so now that we've introduced these additional sources of uncertainty, there's a lot more delay. But I'll still note that all of these regions outside of Antarctica have a color associated with them. So despite all of this uncertainty, we're detecting changes for all non-Antarctic IPCC regions. And the reason we're not seeing it in the Antarctic is because we just don't say that there's enough data availability there. The coverage is not good enough, and so we basically don't trust. Our record only starts recently, and so we don't have that kind of leverage of a longer record to detect these changes. We also repeat this analysis at a finer scale. So now we go to the native 5 by 5 degree resolution of these data products, and we recompute our median and strict time of emergence values. And we essentially see that now there's some regions where we don't have a value. And so again, as you go to this finer scale, you can have challenges with data availability. You can have regions that are especially poorly sampled. And so our ability to detect changes is much less confident at these scales. And I'll also notice that regions that are really kind of dominated by delays in excess over 1 or 2 decades are in sub-Saharan Africa and they're in South America. And so this is really kind of the imprint of historically where science has been done and where observations have been taken onto this pretty important question of detecting surface temperature change. So to summarize, we quantified all these different sources of uncertainty, and we're still detecting changes over essentially the entire non-Antarctic land surface. And even we can kind of look back and show that even when we account for all these different sources of uncertainty, more than 50% of the land surface had actually emerged by the year 2000. So we quantify all this uncertainty, and there's still this really robust regional signal of warming. But also this kind of occurs despite this delay, and we quantify that over 35% of the Earth's land surface has delays in excess of 20 years. So, just kind of tie things up. Started off by showing that there's seasonality in the emergence of Arctic long-wave radiation, and our Earth system model, large ensembles, are a really valuable tool, kind of studying the climate processes and uncertainty in that field. Also, I presented this tool, COSP-RTTOV, for producing, effectively level 1-like fields from our Earth system models that we can compare with these really valuable satellite records of radiance and brightness temperature. And then finally, I used observational uncertainty ensembles in a variety of Earth system model experiments to quantify uncertainty in regional surface temperature detection and show that despite this uncertainty, we have really robust detection of regional warming. And so I think just to try and tie these all together, the way that we compare our models and our observations is really important. We need to think about all these kind of challenges to comparing them, which are both the way that we define our variables, but also the internal climate variability that's just inherent to the climate system. But when we really think about these comparisons, I think there's some really powerful science to be done. And that's all I have. I'm happy to take any questions.
Sweet. Well, I think faculty have had enough questions already, so let's go with students first. If there are any students, then we can come back to faculty later on for extra questions at the end. Let's just start with John.
Jonah, it's really interesting. One of your last slides showed with a higher resolution comparison. One region you didn't mention that I found was interesting, and you go back to that, was central Russia, or maybe it's Mongolia. It's near the center of the, that purple spot on your total delay. A long time to emerge in the signal there. And I'm wondering if there's applications of this kind of analysis that can be done for certain kinds of processes like the winter monsoon in the steppe. And does that emergence of such a signal from the monsoon delayed because you can't get the temperature signal?
So you're asking, does this explain challenges in kind of detecting changes in other fields?
Yeah, circulation anomalies, right, exactly. Is that possible?
Oh, I have not thought about that at all. So you're interested in taking a temperature field and using it to tell you something about...
Yeah, because, this is hopelessly naive, but it occurs to me. That's a region where the anticyclone in the wintertime is an enormously influential feature over the whole eastern part of the continent. And I'm wondering if an inability to detect a substantial trend in the temperature might also mean you can't detect a substantial trend in the way the winter monsoon, East Asian winter monsoon works, because so much of what controls the anticyclone at the surface is the cold temperatures.
Yeah, I think that's a great question, and what I'd want to do, I wish I had an extra slide that showed that kind of plot that kind of showed the uncertainty, because that would be able to tell us, in some cases, the challenge of detecting a trend is just that envelope is much wider in some regions than in others, so it's the internal variability. So to really understand if the delay there is due to processes versus our observational record, I'd kind of dig in to, if I had one of these for that region, I wish I could pull it out right now, because then we could look at it.
Okay, thanks.
Yes.
So your satellite simulator, is a great idea. ARCTOP is great. It's basically what's being done in contemporary data simulation, and almost except for ESMWF, they're only doing clear sky seeding. So my question is, how much both the microphysics in the climate models is still fairly primitive, and the complex graded processes within clouds in the forward model there's also a lot of approximations. How much confidence do you have in that all sky result?
Yes. So the nice thing there is that I only want to be as good as my model is. And so you can imagine that I have a radio transfer model that's running in CESM and is kind of determining the physics of the system. And then I have this second model that's kind of diagnostic, that's meant to compare with observations. I want to be as smart or as stupid as the one that iterates the physics, because I want to represent what's happening in the model. So if the model has a simple representation, I just want my diagnostic model to be only as good as that. Because yeah, the goal is not to, again, then it would be inconsistent with the physics of the model itself. So I'm okay with the rate of transfer of the model being bad, as long as my diagnostic model is just as bad. So then, does that?
How do you compare that to observed all-sky brightness temperatures?
Yeah.
You know there's large errors in the cloud regions.
Yeah. So, what I guess the first thing that we did, both to kind of demonstrate that the diagnostic model is about as smart or stupid as the other one, is that we did actually the quadrature ourselves. So I ran in a single column model, and I simulated basically the EASI instrument at a bunch of different zenith viewing angles, and I did the quadrature and the sum over the spectral domain to compare with the internal rate of transfer model of our system model. So that's how I validated the tool. And then I'm not sure if I'm okay comparing them, because the model is, if the model is wrong, then the model is wrong. So basically, if the model's rate of transfer is wrong and the difference is because the model's rate of transfer is wrong, I guess this tool does not allow you to distinguish that from if the model is wrong because the state of the atmosphere and the state of the clouds is wrong. But this is not, I guess it's not a tool for getting at that specific question. I think that would require, multiple different parameterizations of rate of transfer in the model itself.
I have one quick. First of all, thanks for a really amazing talk, Jonah. Always like hearing from you about the science. So in the first part of your section, you showed the time of emergence for long radiation across the Arctic, and I have just a simple quick question. Like, is there a way to get a regional difference of the same? Like trying to identify locations in the Arctic using the series data, or when you introduce pixel by pixel emergence, then the data becomes unreliable. That's why you did an Arctic.
So are you asking about this, basically?
If this is your section 1, then yes.
Yes.
Yeah, well, sort of, yes.
Yeah,
Okay.
so you're right. I reported values that were integrated over the central Arctic, and we also computed it spatially.
Okay.
And what you see are basically that it's always sea ice. Even in the long wave, it's sea ice. Like these maps in the winter that are showing this really big contrast in the time of emergence are basically looking at like the historical sea ice mass at the beginning of the record, because that's where the changes are really, really large. You lose sea ice, you get a lot more less variability, which actually is not so important here, but you get this emission of energy into the atmosphere and into space. So it's basically like the historical sea ice edge. So if you're asking about other climate processes that mediate this, it's basically the mean state of sea ice at the beginning of the record that's also important.
Well, we're at time. We'll wrap up there. Jonah's here for another 2 months, so if anyone wants to talk about climate model rate of transfer, he'll be here for a while. Feel free to chat to him.
Yeah.
Thanks.
Thank you.